Hello everybody, we are in week 9 of this course. In this week we shall discuss counter. So, we begin with a discussion on asynchronous counter, which we shall take up in this particular class. Before that we shall have a quick recap of what we discussed in week 8. So, if you remember, we discussed shift register and there we noted that the number of bits in the register defines how many information can be stored, digital information can be stored, and we discussed various configuration of it: parallel input, parallel output, serial input, parallel output, parallel input, serial output, and serial input, serial output. And we noted that serial in and serial out gives the option of having less number of input output pins, but the time required for data write and data read is more. And we also noted that for serial data out, the way we read the data in such case as such is destructive, but if we feed the data back, then it will be the data can be restored, rewritten in the shift register. And we saw various application of shift register, serial to parallel, parallel to serial conversion, and then using that to for a serial to serial communication, which reduces the number of transmission channel required, that is required. Then sequence generator, sequence detector, ring counter, Johnson counter, introducing delay of appropriate required time. And then we discussed at length linear feedback shift register and its various use. And as pseudo random number generator, it has various use in from cryptography to many different places. And we also saw cycle redundancy check generation and also detection any error in that code that is code word for any especially it was useful for burst error checking. So, that kind of use also we have seen. And finally, we saw use of shift register in efficient realization of adder cum subtractor, multiplier, divider. Okay. So, with this we start discussion on counter. So, counter, what is a counter? So, counter keeps record of the number of times a particular event has occurred. Okay. So, it keeps a count. So, the way the name itself can give us an idea, and to note how many such event has taken place. So, the counter circuit with the memory element in it, it advances its state one by one. Okay. And one particular state is associated with one specific count. So, there is a uniqueness in this particular thing. So, a specific state is associated with one count, and if this advancing of state is in sequential order. Okay. So, 0 0 0 0 to 0 0 0 1, then 0 0 1 0, so on and so forth. Then if it is advancing, it is increasing, then it is up counter, and if it is decreasing, the other way it happens, it is called down counter. Okay. But as I said, the basic idea is you need to have a unique state. So, it is not necessary that it is always need to be in that manner. So, it could be any random but unique state, but as many number of state, as many count that is required here. So, that is also possible. In that case, it is random or irregular sequence will be there. And the way the events trigger all the flip flops that is there in the counter design, in the make of the counter, it can happen that the trigger is going to each of the flip flop, and simultaneously each of the flip flop can get triggered. So, that is called synchronous. Synchronously it is happening. So, that is called synchronous counter. And if the trigger, the external trigger that is coming, that is going to one of the flip flop, then that flip flop in turn triggers the next, and so on and so forth. Okay, as if the effect of one is going past to the other in a ripple manner. So, that is called ripple counter. Also, it is because it is happening in different point of time. So that's why it is called not exactly same synchronous with the external trigger. So it is also called asynchronous counter. Okay. Modulo n or mod n counter has got n different states. Okay. So that the number, that is the way it is associated, and after n such trigger, after the count of n, it comes back to its initial value. And if there are m flip flops used for counter design, of course 2 to the power m need to be greater than or equal to n. Okay. And usually in most of the applications discussion that we will have, clock is given as input trigger, but it could be some other signal also. And mod n counter is also called divided by n counter. So we shall soon see that the output of the counter effectively will be having the rate of change of the signal, which is original signal, that is the clock or the input trigger, divided by the modulo number. Okay. So with this basic understanding of how counter works or counter is supposed to work, we look at asynchronous up counter. We begin our discussion with asynchronous up counter. Okay. So for that we are having a circuit made up of JK flip flop. We could have some other flip flop as well, but JK flip flop we have taken it up. Okay. So what you see here, that both the inputs of each of the JK flip flop is connected to 1, tied to VCC, that means 1. So each of the flip flop, when they get the trigger, okay, the clock at the negative edge of it, okay, this is negative edge triggered, okay, all of you can see that. So it is supposed to toggle, okay. So that is for sure. Now let us see how things move. So the clock is given here only to the first flip flop, right, as I was saying that it is asynchronous. So the clock is not fed to each of the flip flop, only the first flip flop is getting the clock, right. Then what will happen after the negative edge? So initially all of the flip flops are initialized with a value say 0 0 0. Okay. So after the negative edge comes, as you see the timing diagram, it will toggle, it will become 1. Another negative edge comes, okay. So this flip flop will become 0, right. So then again 1 0 1 0 1 0 and 1. So this is the way it will continue. Is it clear? So this is how the first flip flop will work, right. We will discuss about second and third little later. So the clock is directly connected, the external trigger which is getting counted, how many clock cycles or how many negative edge of the clock occurring, that is going directly to the flip flop A, and the flip flop A is toggling in each of the negative edge in each clock cycle, right, at these points A, B, C, D, E, the way you see it. Is it fine? Now what happens? This flip flop B is getting a feel, getting an idea about the triggering through A, not directly from the clock. So whenever A changes, A output A, okay, uncomplemented output A is connected as clock to flip flop B. So whenever A changes from high to low, right, so a trigger comes, that is serving as a clock, right. Now for every 2 change in the clock, you can see A changes by 1, these 2 cycle, these are the 2 cycles, then A changes by there are 2 negative edges here, then there is 1 negative edge of the clock, okay. So for every 2 such clock trigger, you get 1 trigger out over here for flip flop B, okay. So it is coming via A, right, it is coming as kind of the effect is rippling through flip flop A to coming to flip flop B, right. So at the negative edge of the A flip flop output, right, the B flip flop will toggle, that is the idea. So A B is remaining 0 0 over here for this time instances. So only at time instant B, when it gets a negative edge, it toggles, so it goes from 0 to 1. Now how long will it remain in 1? As long as next negative edge from A comes here because A is fed as clock. So next negative edge A comes at D, you can see here, right. So at the time from 1 1 it comes to 0. So next negative edge will come at F, so it goes from 0 0 to 1 1 and this way it goes on. Is it fine? Okay. Now let us look at C. What happens to C? C is getting triggered from B. Okay. So similarly, whenever B goes from high to low, that time this C is triggered, and triggered in the sense it is both the inputs are 1, so it will toggle. So let us see when B is going from high to low. So B is going from high to low at D and again at H, right. So these are the instances 1 to 0 and again 1 to 0. So C is changing, C is remaining 0 0 0 0, okay, because it has not got any trigger, right. Though flip flop A has got triggered in every clock cycle, B has got triggered in every 2 clock cycle, C has not got triggered up to this, only in the 4th clock cycle you can see A B C D, right. It is getting a trigger, okay, and at that time since it is toggling it goes from 0 to 1 and it remains at 1 till next negative edge of B comes and it goes from 1 to 0 and this way it continues. Is it fine? So this is what is happening to the flip flops, right. Now by this what have you achieved in terms of count? So if you now look at the values of CBA, if you read it in this manner, C MSB, P, C is your MSB and A is your LSB. If you read it this way, so 0 0 0, 0 0 1 you can read in each of these clock cycle, right, up to A. From A to B it is 0 0 1, B to C it is 0 1 0, C to D it is 0 1 1, okay. So these are the clock cycles and 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, right. What is it in binary? 0 to 7 you have come, then again it is 0 0 0, okay. So you have got these states, if you put it in the tabular form, 0 1 2 3 4 5 6 7 and again it is coming to 0, right. So what is it? It is nothing but up count, the number is sequentially increasing, right, and it is a modulo 8 counter because 8 distinct states are there. Now if you look at the output of flip flop A, right, you can see for every 2 changes in clock 1 change is happening here. So clock cycle time period of A, 1 period of A is just half of twice that of the clock period, right. 2 clock periods are consumed in 1 cycle of A. So frequency wise for every 2 cycle, 1 cycle of A is seen. So the frequency of A is half of it, then half of the clock. Frequency of B 1/4 and frequency of C, that is the last flip flop over here, you are having a frequency which is divided by 8. So you can see that divided by 8, it is a modulo 8 counter because 8 states are there. So you can get up to if you from the last output A divided by 8 count, okay, output. So far so good, we have got a up counter, modulo 8 up counter by a very simple mechanism. The output of one is fed as clock to the next flip flop and each flip flop is toggling. Now in this, what was not visible in the previous case, that is the timing diagram, so that we are trying to show by stretching the diagram in somewhat, okay, and introducing the time delay associated with each flip flop transition, okay. So let us see what is it. So this is the clock, right. So clock has got a negative edge over here. Now flip flop A is changing, but it will take a propagation delay which is defined here as T suffix P, right. So after that time only A will go up Similarly, A will go down here after that propagation time, propagation delay Tp, right? Is it fine? So that will happen in every cases. Now flip-flop B. So flip-flop B is not fed by the clock directly, it is fed by the flip-flop A, right? So when flip-flop A changes, after that one more propagation delay which is required inside flip-flop B for its output to change, that will be there. So from the clocking instant over here, the negative edge, B changes, change of B will take place, change of A required, that is one propagation delay, plus change of B that is required. So two propagation delay will be there within this. So that is what is shown here. So two propagation delay will get involved. And for C, what will happen? C is not again fed by clock, okay, triggered by clock, it is triggered by B. So B is taking two propagation delay from the clocking instant. So it will take another propagation delay. So three propagation delay will come into picture. Is it clear? So this way you can see in this arrangement the propagation delay are cumulative, right? And if you are having a very fast clocking, right, then this propagation delay, when they add it up for an n-bit counter, right, and becomes comparable with the time period of this particular clock, okay, then there can be problem, okay. So this addition, when it goes extend beyond this time period, then what will happen? Within this time period over here, never this 100 will occur. So for example, over this is the way you see 011, then 100, right. So this is the corresponding clock cycle, okay. So 0, 1, 2, 3, 4, this is the fourth clock cycles after starting from 0, okay. So 1, 2, 3, 4, right. So this is the fourth clock edges have come, right. But if it extends beyond this, so fifth clock edge will come and 100 is not shown. So that is what is something comes as a cause of concern. So this is one issue with this kind of arrangement, right. Another is what you can see after 0, 0, 0, this is 0, 0, 1, after that 0, 1, 0 is supposed to come in up counter, but momentarily you can see for a small duration 0, 0, 0 is there because A has changed, but B is taking one more propagation delay to change, okay. Similarly over here after 0, 1, 1 you are expecting 1, 0, 0, 0 to come, 1, 0, 0, right, but momentarily you can see that 0, 1, 0 is there and then 0, 0, 0 is there, right, after that 1, 0, 0 is coming, right. So this can cause glitch in the circuit, okay. So this is something which one need to be careful about, okay. And we shall see solutions and many other things before later, but this is something which we take note in asynchronous counter in this discussion, this part of the discussion. Now we look at asynchronous down counter, okay. So asynchronous up counter we have seen. So asynchronous down counter, again we look at modulo 8 counter. These are three flip flops up to with this 3 2 to the power 3 maximum modulo 8 counter is possible. So in this what is done? You can see the circuit input side remains the same. Each flip flop will toggle, okay. Clock is given to the first flip flop, right, and over here the instead of A bar is fed as clock to the next flip flop B. B bar is fed as clock to the next flip flop, that is C. Is it fine? Okay. So by this what happens? So initial state is 0 0 0 and A will toggle in every clocking and negative edge of the clock, that is for sure. This is the first flip flop, right. So that is 0 1 0 1, that is what you see for A, which is okay, which is similar to what you had seen before. Now because of A bar fed as clock, what happens? So this will change at negative edge, right. So A is going from, in this particular place, A is going from high to low, okay. Sorry, A is going from here low to high. So what will happen to A bar? A bar will go from high to low, isn't it? If you plot A bar alongside, okay, A is going from high to low. So A bar will go from A is going from low to high. So A will go from high to low. So there is a negative edge. There is a negative edge over here which will trigger it. Trigger it means it will toggle. So B will go from then 0 to 1. Is it fine? Now when B goes from 0 to 1, B goes from 0 to 1, right? B bar, what happens to B bar? B bar will go, so that was A bar before. Now B bar will go from high to low, 1 to 0. So that will also trigger C. So C will go from 0 to 1. Is it clear? Because it is just opposite of it, right? Wherever there is a positive edge for A, okay, there is a negative edge for A bar. Similarly for B bar, and C bar is not fed anywhere, so it would have been for C bar also, okay, if there was a flip flop D, right? So at positive edges of A, B, actually transition are happening, okay, because for the subsequent flip flops, because A bar and B bar are fed as clock. So this positive edge is over here, so 0 0 0, it becomes 1 1 1, right? Next, this A is changing, right, and A is changing over here, it is going from high to low, and it is high to low means A bar is going from low to high, so no change, right? Understood? Again A is going from low to high here, so output will go from A bar will go from high to low. So here A bar is going from high to low, so there is a change in B, so it is going from 1 to 0. So this is the way it continues. So what you can see, 1 1 1, after that 1 1 0, after that 1 0 1, okay. Again B goes from low to high here, so high to low will be in this particular place, so C changes over here, okay, and C does not change when B goes from high to low, because B bar is what is fed here, unlike the previous case. So this way you can see 1 1 1, this way if you read MSB to LSB, C to A, 1 1 0 1 0 1 1 0 0 0 1 1, okay, and these are the counting states, right? Is it fine? And it is up to going up to 0 0 0, right, 0 0 1, and then it is 0 0 0, after that again 1 1 1 will get loaded, okay, right. So it is moderate down counter. Now one important thing to be noted here, so you have taken output A, B, C, right. Now if inverted output is also available, please understand this part. If this counter circuit also allows you inverted output to the outside world, okay, that means A bar, B bar and C bar, okay. So what the reading for C bar, B bar, A bar would have been in these cases? Can you identify? So for example, this was 0 0 0, right, after that it has gone to 1 1 1, okay. So 1 1 1, and then 1 1 1 inverted is 0 0 0 only, okay. So after that it is 1 1 0. So 1 1 0 is your what? Inverted is 0 0 1, then 1 0 1. So 1 inverted will be 0, C bar will be 0, this is 1, this is 1 0 1, 1 0, and this is 0. So just invert of this, and initially when it was 1 0 0 0, it would have been, initially it was 1 1 1, we are avoiding that. So this way it will continue. So what is it? It is up counter only, up counting. So the inverted outputs, complemented outputs will, if available, will give you up count, while the standard one, uncomplemented outputs, are giving you down counter for A bar and B bar fed as clock to the subsequent flip flops, right. So, similarly in the previous arrangement, the up counter we had seen had with the option of taking the output from C bar, B bar, A bar, then output there would have shown down count. Okay. So, this we again take a note. Now, having understood how up counter and down counter works in a asynchronous counter, okay. So, can we have one circuit, okay, which can both work as up counter and down counter, and depending on our requirement we can make it work like a up counter, and for another use we can make it work like a down counter. So, here is a circuit. So, the flip flops A, B, C are there, the inputs are 1 1, that means for every clocking available here it will trigger, okay, it will toggle, okay, it will go to the other value. If it is 0 it will go to 1 1, it will go to 0, okay. Now, we have put an additional input M. So, M can be considered as mode, okay, control input. So, if M is 0, what happens? Let us see for this particular circuit, right. So, M is 0, you can see M here, this is 2 AND gate and 1 OR gate. So, it is more like a 2 to, I mean it is the way the 2 to 1 multiplexer circuit you have seen, but in a different context, right. So, M is equal to 0, this means this is equal to 1, right, this is equal to 1 and this is equal to 0. So, 0 means this AND gate output is 0 irrespective of what is there in the other output, okay, because for AND gate 0 is a forcing input, and since it is 1, for this AND gate whatever it changes in A, that will go here, right, and for OR gate 0 is a non-forcing input. So, whatever change is occurring it will come here. So, effectively M is equal to 0, A is coming here, similarly B is coming here, right, and if A comes and B comes, the way we have seen the circuit, it is up counter only. Instead of this, if M is equal to 1, this is 0, so this is 0 and this is 1, right. So, this is 0 and this is 1. So, what is happening at that time? A bar is going to the clock of B flip flop and B bar is going to the clock of C flip flop, right. So, what is this arrangement? If you are taking output from A, B, C, the uncomplemented output of each of the flip flop, okay. So, then it is acting like a down counter. So, M is equal to 0 up counter, M is equal to 1 down counter. This is the way we can make it work, okay. In one circuit both the things are there, right. So, while it is counting, it has counted up to particular level value, then you are changing M, then again it will start counting in the opposite direction. So, it has counted in the up count mode 0, 1, 2, 3, 4, 5, okay, and then you have made it 1. So, it will start down counting, okay. So, finally, we would like to see one standard IC which gives this asynchronous up count, okay. So, IC 7493 is one such IC which has got actually if you look at the inside the circuit, a mod 8 counter over here and a mod 2 counter, okay. Two such units are there in this particular IC. So, this is clock B and this is clock A, right. If you do not bother about clock A, right, if you just feed the outside clock to clock B, then what will happen? This circuit will behave like a mod 8 up counter. You can see this QB is going to the flip flop, QC is going to the flip flop. So, it is not complemented output. So, it is uncomplemented output is going. So, it will be behaving like a up counter, right. So, this part is mod 8 up counter and this part is mod 2 counter, right. Now, instead of QD, if you are just looking at QB and QC, then these are mod 2 and mod 4, right. You will get a count of that thing. You have seen that before, that it is a divided by 2 over here, divided by 4 over here and divided by 8 over here, okay. So, that is the one, but as a whole 3 flip flops are there, 8 unique states, increasing order. So, it is a mod 8 up counter if you take it as a whole, right. Now, if you make an external connection from QA to clock B over here, right, and feed the clock here, external clock here, then what will happen? So, now forget about this one, it is not there, it is directly connected. So, instead of 3 flip flops, now we are having 4 flip flops. So, in the earlier circuit timing diagram, we stopped at A, B and C, then there will be a D coming over there, right. So, that D will change for every negative edge of C, okay, and that will, one full cycle of it will occur for 8 plus 8, 16 cycles of the clock, right. So, it will become a mod 16 counter, okay, because every here when you are feeding the clock. So, if you remember the circuit. So, this is your clock. So, negative edge, okay. So, the QA is changing over here and then again over here and then again over here, right. So, this is halved. So, this is divided by 2 and this is divided by 8, right. So, together it is divided by 16. So, modulo 16 count, that is what we will get, right. Is it clear? So, extending what we had discussed before for 3 flip flops to 4 flip flops, right. Additionally, here you can see there are 2 other inputs which are R01 and R02. If both of them are high, then what will happen? This is an AND gate, so it will become low and you can see that there will be asynchronous clear, okay, asynchronous reset, right. Okay, it is required for initialization or for some other purposes that we shall discuss later, and any one of them low, okay, then the normal count operation will take place, up count operation will take place, right. And why 2, why not 1? 1 would have been sufficient, okay. More on that will be revealed in the subsequent discussion on the counter, okay. There is a specific reason to put this thing, some such thing, okay, which is helpful in certain context, okay. So, to summarize, counter keeps a record of the number of times a particular event has occurred by advancing its state, which is unique for each count. And for modulo n counter, n different states are there, and if m flip flops are there, then with those m flip flops we can go up to 2 to the power m modulo number. Asynchronous counter, the clocking of consecutive flip flops are not from the same clock or the external trigger, it is done through a rippling effect from one flip flop to the another. In up counter, the counting states sequentially go up, and in down counter it is sequentially come down, okay. And if you have the option of taking the output from the inverted outputs, then the counter of opposite kind can be available. And in asynchronous counter, important thing is that you have seen the propagation delay is cumulative, for which when this cumulative delay is of the order of the clock time period, then a count can get missed, and also it can give glitch, in between values may come up, okay, which can cause problem. And up down counter can be made where one same circuit can give both up count as well as down count by suitable choice of control input. Thank you.